So anyone here didn't even learn Rust? Never ever. All right. So I just want, maybe some people already know that because I already shared it on my Facebook. So my journey is here. You guys can hear me, right? If it yes, I'm not gonna use the microphone. My journey is in Rust begin like almost 3 years ago here in this room because of the guys who just give a talk trying to convince you to do Rust. So we have like in Agoda we used to have, I think we still have, right? But I don't know because I already left the company for like a year. We have Tech talk, and one day the Idan coming into chatting session like, how do we speed up the data transformation in the pipeline? So usually when we do like a canary deployment by in the system, so you need to wait for sometimes maybe like 30 seconds or 1 minute, and then to wait for the data to do some things like transforming something like that, to be going to the graph to the dashboard, and then we lose in that 1 minute if anything's happened, right? It's been like every transaction is going to the canary pot or canary machine is gonna affect customer already. What he do is that he transform it from, I think it's Scala to Rust, right? And it speed up from like a minute to just like less than 5 seconds. And that's when I start my career with Rust, and still regret sometimes because I'm fighting with my best friend a lot, the compilers. So my talk is gonna be about the Lambda calcuRust. So this is just like the sequence of my another talk is coming from like the future. I mean, futures as a futures, asynchronous programming in Rust, right? So another things that I encourage people to learn after like, okay, you already know like ownership, lifetime, other things. You already know like how to do asynchronous programming in Rust. Other things that is pretty cool in Rust is the functional programming features in it. So what is this talk about? This I'm gonna talk about the origin of the functional paradigm, right? What is it? How it affect our programming world? And I'm gonna represent it into the in terms of the map to the computational and the FP in Rust. That the whole things I'm gonna talk today. So first question: what is functional paradigm? Anyone knows who is this guy? No. Okay. This guy is actually this guy. His name is David Hilbert, right? So David Hilbert, he is the curious guy. He used to ask a lot of questions, and one of the questions, this is one of the famous quote that he has. The Vermusen Wissen, where Veden Wissen is mean like we must know, we will know. And he have like the things that make him famous. One of the things that he asked around like I think 73 questions about the question in mathematical terms in the mathematical philosophies, and all of that mostly I think all of it inspire the modern day math. And one of the questions is this one. It's the Entscheidung problems. This is the question. So easy, right? I think you guys understand, no? Okay, so simplify is a bit still hard, right? So this is oversimplified, but I'm trying to make it easier to understand for you guys to understand. This is the question that make us here, make every of us sitting here doing a job that we love. So there is a word in here. It's David Hilbert asked the question that, is there an algorithm that will take a logical statement and be able to answer yes or no, depending on the truth value of the statement? So it's kind of like, if you want to ask, there exists the algorithm when you give something to it, and then you always get the answer yes or no. That is his question. So the thing I want to highlight is here is an algorithm. Because before David Hilbert asked this question, there is no real definition of an algorithm. Algorithm exists as long as we are here, right? As a human, there is a lot. There is like just execute some things like when your mother told you to go into the shop to start to buy a milk. That's already the algorithms, right? But there is no what should I say? Pure define, like a good define of the algorithm before that time. So to answer this question, you need to define the algorithm first. You guys familiar with this one? Anyone? This is the things that important to us as well. It's the fundamental of all the things that we do. In every modern world. So if I give a hint, it's coming from this guy. This guy is Vatulin, and this is the formal definition of Turing machine. Right? So Turing machine said that to define the algorithm, you need to do some compute on it by changing the state, transition on left to right, and then writing into the tape, right? Actually, before this guy can solve the problems, answer the Hilbert problem and Schedule problem, there is another guy called Alonso Church. This is the guy. He is the one who invented Lambda calculus. This guy said that if you want to solve the algorithm, you need to do it by recursive pattern matching and rewriting it. So we're not gonna go in deep into that, but these two guys, just know that they solve the same problem within like pretty pretty close to each other. But at that time, we do not have any Facebook, we do not have any messengers, right? So this guy, the first guy, he is live in the United States, and the other Turing live in the British, right? So after like a year, when they already print out their papers, so Turing already checked that the Church theorem, the things that the lambda calculus that Alonso Church just invented to solve the problem. He just thinks that these two things can be equivalent. What do you mean by that? So Alan Turing going to the United States to be the PhD of the Alonso Church, right? And doing the Church Turing thesis, which is they found out that the lambda calculus and Turing machine is equivalent. What does that mean? This is the computational universality. It means that everything that can write or can express in the Turing machine things, it's always can be represented or expressed in the lambda calculus as well. That is the big things, because that means everything that can compute is going to be equivalent for both lambda calculus and Turing machine. And 1 eternity later, this guy, we already know that everything that Turing, everything that in our modern day, like the computers, your mobile phone, actually air condition, it's coming from the Turing machines, right? The things that he, what should I say, like the foundation of the computational. But why we do not use lambda calculus? Because this one is more practical, as you can think, right? Because when you do something, even if you do the lambda calculus, you need to write down something to short note, right? So this is more practical than these things is in everyday life right now. The lambda calculus also, because we know that lambda calculus and Turing machine is the equivalent to each other, right? So we know that the machine needs to be the Turing things, but when we do the programming paradigm, it doesn't need to be the imperative one, right? Turing machine is the imperative one. I can say like the functional paradigm is like kind of a declarative one. We can say something like that. So there is like a lot of functional programming paradigm. The one that the famous is called Lisp. The one that look like a yin yang is a Lisp, right? And then in the modern day computers, in the modern day, all the programming language, I love to represent everything into the Haskell. This is a Haskell. It's pretty, as far as I know, it's the most functional paradigm programming language that I know. So this is the Haskell is naming after this guy. He is the Haskell Curry, which is the PhD of the Alonso Church, I think, if I remember correctly. So coming to Rust, we already know that Rust is building pretty near the machines, right? When I say pretty near the machines, mean like some people consider it's a system language, right? When I say system language, it's like it's the language that can create some things for the system. Like right now, it's already accepted to be one of the languages in the Linux kernels, right? Also Android OS as well, and also like a lot of my friends use it for the embedded system. But because we already know that the Rust creating for the imperative machine. So Rust has a lot of inspiration from the Haskell. So this is the purpose of my talk. I take like 10 minutes to introduce like the purpose of my talk. Lambda calculus, when the functional paradigm, which is like here, meet the imperative machine, which is like here. So because of these two things is equivalent, but when you need to compile when you need to try to compile the functional things, the algorithm that express in the functional lambda calculus to be the imperative. sometimes it's easy, but sometimes it's hard. So when the language, which is basically design, is an imperative language by design. I can say I like to say this is the I talk with my professors and then he give this thought and I really agree with him. So the last is pretty like imperative language by design. But the things that is pretty interesting is that if what is functional paradigm gonna do or gonna represent or gonna affect in the language is within the system. So okay, so we already know that Lambda calculus is the heart of the functional programming, right? But the things the things that I'm gonna talk is not just Lambda calculus, but everything's in the as the foundation of functional programming language. I mean, functional programming paradigm is coming. You can trace back to Lambda calculus. So the first thing we're gonna refer. This is just like a concept. The disclaimer that I'm gonna talk to first. That the things that we're gonna talk is type system. Is a type calculus, right? And a type calculus you can map it to the categories because every single type calculus is a cartesian coarse categories. This is a disclaimer, so I can tell you guys like, okay, some concept is not mapped to the Lambda calculus directly, but you can trace it back from like category series back to the type calculus, back to the Lambda calculus, something like that. And in this talk, I'm gonna trying to represent the math. I'm gonna try represent the math into the Haskell one because even if like the functional paradigm, it's coming from a math, right? But after it's compiled or when the computer guys or when the programmers or computer scientists use the concept from the mathematicians guys, they need to simplify some things. Some context gonna let out. So some context is still there, like the big concept still there, but some concept is gonna let out. So I'm gonna trying to represent it from the math to computer science by using the Haskell. And I'm gonna compare between these two things, the math, the Haskell, and the Rust. Okay. So why do I choose to represent my talk like this? Because when you're asking, let's say if you're new to functional programming and you search this in the Google a lot of time, you're gonna see these things, right? A lot of people, a lot of articles are gonna say like, okay, functional programming is to write a function with no side effect. But why? What is it? So just going quick. So the function, it's the things when you have a domain, right? And you have some things in the domain, you have a codomain, something in the codomain, and everything's in the domain map, like many to one or one to one to a codomains, right? And this is and the arrows we call the function from A to B, right? And this is what computer science call it a pure function. But actually, these things for the mathematicians guy never consider a pure function because function is a function. There is no pure. There's no things like pure or not pure, right? So because it's a pure function, right? When you say like when you write some things with no side effect, it means like you cannot make if you give some input into the function, it should be always have the same output, right? So Rust have these things called immutable by default. Boring, right? It's really easy. Everyone knows that. I'm pretty sure. So let's go up a bit. Higher order function. So what is higher order function? It's in the math things. Higher order function is, I mean, in the maths and computer science. To simplify it, it means like the function that you can take the function as a parameter and return the functions, right? So let's go. This one is in the time calculus. It's gonna represent as the this guy. Just forget it a bit. I'm gonna talk about it later. So some people are gonna say like this is a function as a first-class citizens, right? Okay, let's take a peek at Haskell function. This is the filter. By the way, the type is mean like in the for the function give me for the function type is mean like give me the type of the things that give it to the function. So the filter have a function as a which to bool and then return some a. So it's pretty much like this, right? What is it? Actually, the Haskell because it's really pure functional, right? So when I say a to bool, it means like that's a function, right? It's a function that accept a, return bool, and then you're gonna give some. Actually, this is a list some kind of list A, and then it is going to return a list of A as well. A is a type. Let's say A can be an int, and then bool can be like filter the event. So the event type is the get the numbers A, return the boolean, right? And then it's gonna return and it's gonna get some list A, and then return another list A, list of int after it filters, right? So it's like this. Filter when we do the filters, event give the function first, and then give the list after, and then you got the result. So this is pretty much, I mean, as you can see, the Haskell, they treat the function as a first-class citizens, right? It's because the first thing that they accept is a function. Not like I believe like a lot of people here, especially the guys from Agoda, like you can write the Scala, right? So like the Scala or others language that trying to do, I mean, using the functional paradigm to embed it in its own language, it's gonna tie it with the object. But this is different. You're gonna accept the function first, and then you accept other things. But actually, it's a type. This function A bool is a type. List A is a type. And list A is a type as well. So next, what is the higher order function in Rust? So if we reinvent the filters, it's gonna be like this. Filter can accept the predicates, right? And then it can accept some objects and return some object as well. So because in the Rust, we do not have list here, right? So we use vector instead. Predicate, we can define predicate as the function using the thread function, which means like this function is gonna accept the int, right? I32 and return boolean, and then just like this, we're gonna execute some function in here. Easy, right? Next. So this is the P. This is what we need to do. We need to explicitly tell that, okay, this is a function. And then next. This is when the imperative machine meet. I mean, when functional paradigm meet the imperative machine, because function in Rust is not straightforward as others. I mean, when you do the higher order function in other language, you just passing the function in it, right? But in Rust, there is things like, okay, this is just like the event, you can pass the event when we call it, you can pass it in here, and then it's gonna filter as we do in Haskell, right? So I cannot remember my things. Oh, okay. Sorry, I skip the slide bit. So in Rust, we can accept the function as a parameters, right? And we also can be able to return a function from the function as well, like this. Okay. So we do it like this, so we can just like passing the this is a function multiply, right? Multiply by, right? When we pass the 2, it's gonna create a new function that gonna take 2 as an A already, right? And then it's gonna wait for another parameters here, and then it's gonna be like a double, right? So when we call a double here, double 5, it's gonna be 5 multiplied by 2, right? Also the triple multiplied by 3 is kind of like multiplied by A is 3, right? 3 is already here. We pass 6 to here, and then it's gonna be 18. So this is the another things that when functional paradigm with the machines, you will see this a lot in Rust. Why we need to move? Because when we create a function, we need to. This is closures, right? We need to move the closures to be owned by a double and to be owned by a triple. It's a function created by a function. So next, yeah, like I said, if functional paradigm you can use it. So this is what I'm trying to say like 2 minutes ago. So in another language, you can just passing the function in it. It's just like you have only one thread called functions, right? But in Rust, you're gonna have 3 things called function mule, and function once. So what is it? Function once, it's the subset of function mule is a subset of function. So function is a big. So if it like the what is it called? Euler. I just cannot remember the name. When Euler things. So function is a big one, right? And function mule, you can do some things with function mule just less than the function one. The function once it's in the function mule again. Why? So let's see this. This is the thread when this is from the Rust documentation. So for the function once, right? You can see like function mule it's the sub thread of the function mule, right? And this also you can trade like why function is the biggest one by the code. But actually because when you call the function once, it means like for the you declare that this function is going to consume something, some context just one time. That's why it's called function once. Function mule is mean like you're going to consume some context and you're going to change it in that function. So this is last compiler needs to know. You will see this kind of thought in the last code, like in the iteration as well. Like when you're playing with like the data is already moved or not, it's the same concept from the ownership and other things. And that's why we in Rust we cannot just have like a thread function. So because I have a lot of slides, I'm gonna go quick after this. Okay. Oh, some people may already notice this one. This one is called currying. Currying is a pretty cool concept in functional paradigm as well. Can we be able to do it in Rust? Let's see. So take a glimpse at the currying first. What is currying? This is the currying. It's hard, right? So I'm gonna simplify it. So the type of the curry. This is the type of the curry. Curry is kind of the function, one of the function that you can call in the Haskell as well. So it accepts tuple. This is a tuple, right? Accept some things that gonna accept function that accept tuple as C parameters and then return some type C out of it. So everything in Haskell is a type. This also is a type, but we can see that this type is a function. Actually, everything in Haskell is a function. If we see just only A and B, it means like function which accept A and return B. So kind of in the function in Haskell, it means like every function will take one parameters always. Okay. So let's see if I define the multiply as things like this, you will see like this multiply is going to accept. This is just one. Like I said, Haskell accept only one parameters, right? This is one parameter, not just like any other language, right? Because this is these things called type, called tuple. Haskell will recognize it as tuple. So this is the type of multiply, and then when we query it, it's gonna break down the tuple into a function which accepts one function. Why it's important? Because if we have things like this, it's pretty easy to compose new things. You can compose a function from the function and always doing the things like that. Like going forward, you can have like, I think I have some things here. Okay, this is unquery, it's the same thing, just doing the backward, right? So, okay, this might be helpful. So, because when you have a querying, right, you have multiply by, as same as the example that I write in Rust. You can do it by like if I want to have another function called double, I can just do it like multiply by 2, and it's gonna give me another function which is accept type A. Num A is a constraint, so it's gonna accept A and return A. So in the multiply by, it needs two parameters, right? It needs A, it needs B, return A. But after I give to it, double is gonna just need one more arguments and return the resource, right? So like double 5 is 10, double 6 is 18. I did not say it in here. So in Rust, in Haskell, we can say like the Haskell function is curry function by default. Every function in Haskell is curry one. So the Rust have currying. It's a cool concept. It's really cool concept. If you understand the currying, it's mean like you can create your own. It's just like you're doing a Lego, right? You can write down the function as small as possible, and then you can have a lot of Lego in your hand, and then you can just building a new function from a Lego function. But is it really cool? Can Rust do it? Rust can do it by 2 and 3 arguments, but ugly. Why I say ugly? So this one is I already showed it here, right? And I trying hard like before I find this solution somewhere in Stack Overflow. I try hard like 30 minutes trying to do the function that can accept the function that can. The function that return the function that will return another function that produce another function. It's pretty hard. This is a nightly one that you're using the unblocked process. And I give up. I did not dare to take a look at trying to do like 4 argument or 5 argument. But in the pure functional paradigm, you can have like 20 argument. It's up to you. Okay. The next one is map. Take a look at map first. This is the last map, right? I think a lot of people, you guys already familiar with it, right? This is a map in the Haskell. Like before, this is the currying, right? That means if I take just only this one, f map and plus 1, I can create a new function called add 1, something like that, and then which accept list kind of list type and then gonna produce something like this as well. But let's see, go back to the map. What is map, right? So the terminology map is pretty broad. It's pretty generic. Kind of like you can. It's kind of a like this one is kind of sometimes it's like pretty generally and not formally defined. But in category theory, we a lot refer it to morphism. So what is it? A morphism basically it's the more general term of the function. So I talked about the function before, right? And the function is kind of like domain. You have a domain, you have codomain, you have some map in it, right? We can call it morphism as well. But in the category theory, actually, I think we're going to talk about category next. Okay. So what is category theory? Because we found a lot of category theory buzzword here, right? So let's take a look. Just a super oversimplified category theory. Okay. So what is it? Category theory is it's a pretty broad concept in mathematics in the math field. The things that they're trying to do is that they're trying to simplify. They're trying to generalize things and trying to see like is everything in the world can break down into category and see the morphism, which is what should I use? Is kind of like relationship between the object. Can we do it like that? So like it sounds pretty easy, right? But actually, you guys know as a programmer, we all know when in doubt, we have a rule of thumb is that when in doubt, we're gonna go specific way, right? Let's say your boss say like, okay, please do some things. We're gonna go specific way first. We're not gonna trying to generalize it because we already know, right? Generalize is hard. This also generalize is hard. So back to category theory, right? We have the object. And we have the morphism. Morphism is the relation between object, right? And also in the morphism, we're gonna have like what is called endomorphism. Endomorphism is mean like the relationship that the morphism that is going back to the object itself, right? Just remember the name. It's gonna play a big part in my talk. I mean, in the functional world as well. So this is called category. Easy like that. Category can be anything. Category can be a city as well. And the morphism can be the way that you travel from one place to another place, like from Bangkok to Singapore, right? So how does the concept of the map from category theory apply to functional programming? I need to claim that every map in the function in the programming language world, I mean, it's coming from the F map. Actually, it's not just a map. It's called the functor map. So again, see, this is the type of the functor, right? It's gonna accept some function that take A, return B, and then functor and then return functor A, and then take functor A, return functor B. So another one, general introduction to functor. What is the functors? This is gonna play a big part in the programming world as well. I don't think it's gonna make it in time. Okay, so functors. Functor is the mapping between categories, right? So easy. So let's see the definition. This is the big picture of the functors. I'm gonna break it down from the definition to these pictures, all right? So first one, functor is the let's see and D categories, right? So this is the category C and the category D. A functor from functor F from C to D is mapping that associates this type of object X in C to object F in D. What does it mean? It means like every object in here, like A, is gonna be mapped by the functor A. Object B gonna map by functor B as well, also C as well. Another one, associates morphism Fxy in C is gonna F blah 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 blah. It's really long. So basically, this one told like every identity is every identity morphism. Identity morphism is the endomorphisms, right? It's gonna be like this. Every endomorphism here, when take the functor, it can be mapped as well. Another one is called for every function for every morphism here. This one called tau. I think this is a sigma and this is tau. So this is a function A to B. This is morphism of A to B by morphism by function sigma, right? So for every function, it's gonna be part of the functor as well. What we can tell about this one, which is like if the category theory can apply to almost everything, you can you can pass everything from one category to another category. Let's say if I have a category of booking, right? And then I have another category of payment. It means like if I know what functor is it, I can transform everything by this functor from the booking state to the payment state. Some kind of that. This is again oversimplified. All right. So this is why the functor is it accept AB and then FA FB. Why is it in here? Is this functors? It's this one, and this one. You see this one? This is the morphism in the category of C, right? So it takes the first morphism in the category of C, and then when it apply the functor, take the object A, have a functor A. It's mean like when you take the functor can be morphous. It's the same as this morphism by the functor morphism, and then going to be the object like functor C. Okay, in Haskell, list is a functor. So some people might know. So the disclaimer is that list is also a monad as well. But in this step, we're gonna talk about list is a functor as first. All right. So why I have this slide? Okay, next. But Rust vector is not. Rust vector is not a functor. Why? Take a look at these pictures again. We have this one. It's called iterators. I believe, and I'm not an expert in the Python, but I believe in a lot of languages that have this kind of things. They're gonna use the iteration to helping to create a map function, right? So that it have a side effect. Why? If you see the iterators, iterator have a function security. This one is a most important function in the iterators. It's called next. Next is mean like let's say you have the iterators, right? We have a list. Next is mean like give me the next item in the iterate. You can see that like here, it's gonna take mutable self into the function because it's gonna when you do some things, this function is gonna do some things and then changing the item and return the item to you, which means like this is not pure function because the concept of the pure function is that you should have no side effect at all. When you do the map, it should be like map as the whole domain to the domain. If you want to map a list, it should be list A map to list B, not iterate everything in A map to another object in B. That's just like that. And again, it's just like a function. Function means function once. The iter have these three things as well. Iter move into iter. So it's kind of like what should I say? Into iter is kind of pretty flexible. Let's get back a bit. This function is doing well when you have a list. You cannot iterate the list right away, right? So you need to have another function to transfer from a vector. Vector to iterate. So these three functions is called into iter, and iter mute. So this one is pretty flexible. It can be give you the value of the iterate or the pointer of the iterate as well. Dependent on the the iter. No, not the into iter. Into iter is sorry. Let me rewind a bit. Into iter is the thing that is gonna give you the value, which is like when you consume, it's gonna be gone, right? Because as ownership, when it's going to the scope, it's gonna be gone. Into iter, actually, the into iter is the one that is pretty flexible. If you do it like this, if you call into iter from the pointers, you're gonna get the pointers and you're gonna get the reference as well. And intermute, it's the same thing. It's kind of like you're gonna get the reference, which is mutable, some kind like that. Still, this is the same as like the function. Like when you need to think about memory, the things that you're gonna use, like in the Rust, which is not happen in another language. I never see it as far as I know. So another things which is pretty cool is called algebraic data type. For me, it's like the most powerful functional concept in Rust. So what is it? Is it like a kind of composition type which formed by combining other types? There is two big things. Again, oversimplified, but we talk I mean, in a lot of I think it's all the time we're going to use just only these two types, the product and the sum type. What is it? So the product type is basically a tuple. Just that. It means we can just simplify it by thinking like product type mean and. You can use and like when you have two types, right? Because data type is kind of like combining other types to create new type, right? So if you have like two types, let's say type A, let's say we have type A, which is coming from type B and C, which it means like type A need to be B and C, something like that. And one of the things that it's product type, and we know, and it's pretty famous, right? It's a tuple. So, but the things that we're gonna focus on is the sum type. This one is pretty powerful. So the sum type is kind of like it contains several different but a fixed type, but you can use only one type at a time. What does that mean? So I'm gonna create both Haskell and Rust here. Let's say we have a shape here, a shape which is this is a sum type. In Haskell we can do it like this. So this means like shape has two. It can be two types, circle or rectangle, right? And then we want to have another function called surface to compute the surface area. So we need to put some things in the circle. I mean, we need to define kind of like a properties of the field into the circle first. And this is actually just like this is pretty cool. This is enumerables, right? But you cannot do this thing in another language. I cannot remember which language you can use it, like C#, Java, Kotlin, and other things you can do it, right? But in Rust, they designed to make the enumerable to be algebraic data type. It's pretty close to this one, right? So this is a function in Haskell. We create a function in Rust like this as well. This is just kind of like pattern matching. When you declare some function in the functional paradigm, you do some like Lambda calculus. I also just say it's going to do the recursive and pattern matching, right? So this is pretty much the same. Using the pattern matching, which is the pretty powerful things in functional paradigm as well. So let's call it. We can just call it like this, and then get the result the same. Next. Okay, this is just like a quick one for some people. Maybe you're gonna have a question. What is this? The last line Haskell is mean like it's gonna make you can treat it like you have parentheses here. Just that it's called applicative. So next. We want to do because Rust is a strong type system, right? So we can do something like this as well. We already know like the circle. This function, this type circle, when we take float for float, it's mean like the first two things. If you can see it here, actually this is the coordinators on the graph, right? This one also rectangle. This is a coordinator on the graph. You can have like two coordinator on the graph, and you can write down the rectangles, right? The same idea. So we're gonna expect this type to be a point. Yeah, so right now shape is gonna have like a circle gonna have a point and a float. This float for circle is the radius. I mean, in the middle of the circles, right? And then we can just what should I say? แทนที่ภาษาอังกฤษว่าอะไรวะ แทนที่ replace. Yeah, replace. We can replace everything into from the things that it should be a point from to be this one, right? And this is possible because this is the type system. So for this one, after we put a point in here, it just see like the normal programming language, right? But you use it without knowing that this is coming from a type theory or type system, which is actually pretty cool after you know the reason behind it or the paradigm behind it. Okay, next is just a call. Okay, so my last thing that I'm gonna talk today is a flat introduction to monad. So it's not easy. So that's why I say like, okay, this is gonna be a flat introduction. A lot of things is gonna be oversimplified. But why I want to talk about this because with these things, algebraic data type with the sum type like this, it's enable us to be able to create the things which is not a monad but act like a monad, and it's pretty cool. Okay, so let's go. Okay. So what is a monad? Monad is just a monoid in the category of the functors, right? So it's easy as that, right? But actually, it's not. This concept is not actually true. Actually, a monad, the correct word it should be a monad in X is a monoid in the category of endofunctor of X. So pretty hard, right? So a fast introduction. So first, let's see what is endofunctor first. We already know that this is a categories, right? This is a functors, right? So what's it? See endofunctor. You can see it here. This is the morphisms, right? Morphism between the object in the category of X, right? And then we can have these functors. It's kind of another morphism, but treat an object as a category, right? So functor and morphism actually pretty much the same, right? So category is kind of like when you going up higher enough, you're gonna see everything just like a dot. So from it, the things here you might when you go down a bit, like when you're on the plane, right? Sometimes you're gonna see like the whole football field, and you can see the people in there. But after you're going up pretty high, you're gonna see the football field just a dot on the earth, right? It's the same. So if we treat categories of X as just one object, right? Okay, this is morphism have endomorphism. I already told about that, right? So functor also can have endofunctor as well, because of this is a morphism, but it's a morphism in a different layers, in a different level. This is a morphism in the category some things, and this is the morphism in the category X, which is can treat as an object as well. So what is the category of endofunctor? This one, we know that category of X can have endofunctors, right? And it can have its as many as it get. Category of endofunctor is usually like this. We pick up every endofunctors, make it into the category. So it's already category of endofunctor of X. All right. Then what is a monoid? Monoid. This is the definition of monoid. They have two things. Just forget the hard word, math words. Just see these two things. It's called associativity and identity element. All right. So as simple as that. In the math, we abstract it a lot. So let's say identity is ID, associativity associates, right? How can we make this category of endofunctor to be a monoid? Pretty easy. Just give it the identity and what should I say? Just like you just think like it's already have the identity and associative already, so it will be a monoid. So right now, we already have a monoid in the category of endofunctor of X, right? And we get when we have this word, this sentence, we already got the monad. This is a monad. Easy as that from the back world. But how we apply it to the real world in our programming language? So introducing the monad in Haskell, because I think it's more easier to explain in Haskell. Actually, this one is the explanation that I got from the YouTube channel called calcuRust. It's pretty cool, and I think it's like the easiest one that I can get from the YouTube channel. So the whole thing is you can just search the monad and like typing like calcuRust. It's the same things that I'm gonna talk in here. I play some things with it a little bit, but most of the idea is coming from them. So this is the data type in the Haskell. We have a data expression here, right? We have some type. The first one is while. The second one is if. So the things that we're gonna trying to do is here is gonna evaluate the expression to do the calculation for us. So function evaluation is gonna take the expression which is contain the first data type is called while. The second one is called diff, right? And this function have a pattern like this. If we give them the while, it's gonna return just only n, return itself. Just this, right? Because it's just like evaluate and bit the same things. But the diff is a little bit complicated because we need to do the recursive to call the eval again. Eval of x, right? Because this x actually this x is an expression, right? So it's gonna need to evaluate again. It's gonna call while n. So in here it's gonna return x, and for y it's gonna when we do the eval y it's gonna return y, and then we divide it. So when we call it, it's just like it. This is the same as doing while 5, but this is the same as doing 6 divided by 2. So this is called 3. So what is the problem with this one? We know that if y is 0, it's going to be like this, right? It's going to have expression divided by 0. And this is called effect, right? This is an effect. So how are we going to deal with it? We're going to do the save dip, save divide, which is instead of returning, instead of get to in, right, and return in, we return maybe in instead. Or we're gonna get back to maybe in later. What is it, right? So what we do is that this is the type of the maybe. They have two sum type. It's called just and nothing. Right. So this is the implementation of SafeDiff. So what we do is that we check first if m this is the function method signatures, right? Function signatures, right? Is get n as the first parameter, m as second one, and we check that if the second parameter is 0, we return nothing. If it's not, just return n diff m, right? Easy. So next, okay. So the things that we're trying to do here, for SafeDiff is already there, but the whole concept we're trying to build it on this expression type by doing the evaluations, right? So we need to transform our evaluation function a bit as well. So instead of return in before, we return maybe in instead. In here, the first one, if it will evaluate the n, evaluate the n, we just return just n. Instead of n, we return just n, right? And when we do the diff, right now we need to specifically tell that it should be either some type for the maybe, which is nothing or just, right? So if we can evaluate x, we can evaluate n again, evaluate y using x, using n, using just n. This is the data in the n, right? And then evaluate y again. If we can evaluate y, we're gonna use m, and then we're gonna use SafeDiff on n, n and m. All right. Next. After this, that means we pass the zeros already. We already be able to pass 0 in the evaluation eval functions here, right? Because we already implement the maybe, and we already have the pattern matching here that call that okay. Both of it need to be the return type need to be maybe, and then SafeDiff is return the maybe, right? So this one, if we have just like this, it's not gonna return. It's not gonna going to the nothing case always, right? Because you can because when you have an n as a type wall, it's always go this one, right? You can always have something to evaluate. So I play with it a bit. Let's say if we can do the pattern matching here as well. Let's say if the numbers of n it's less than or equal to 2, we're gonna return nothings here, right? So which means for this function, if it's 2, you cannot do it anymore. Everything is going to return as a nothing, right? Okay. So we can see that there is 2 things that is duplicated here. As a programmer, we do not like it, right? We trying to extract the things that that redundant to be other things. So there are the things in here. There are the things in Haskell called binding, which is this one. The binding have this kind of type. You see, this kind of binding. It's gonna take monad A, and then take some function which is take A, return monad B, which is gonna transform A to monad B and then return monad B, right? Some guys who familiar with Scala might already notice this one. This is fat map. So the binding in Haskell is a fat map, right? Okay. So bad. Yeah. So I gotta go fast because the guy behind me said that I need to wrap up. So we can do all of that. We can extract all of that into the binding here. And this is a lambda. This is in Haskell. This is a lambda symbol, but it's used just a slash because this is look like lambda, like the most thing in your keyboard that can look like a lambda, right? So this is the anonymous function. It's a binding. If we got the x, we can got n, right? And we're gonna evaluate y again. If it's not nothing, it's gonna return something that we call SafeDiff, just like that. So it's gonna from here. This is if you guys coming from Scala, this is in Haskell we call is do notation, but it's the same as for comprehension in Scala. Here, just make it to be able to read it more easier. So we can say like maybe it's a monad. So this whole thing that I express to you here, we just reinvent the monad, maybe monad on the eval function. So, and how it map from the function to the things in map here. You can see this one. When you do the maybe can return itself as well, but I use this picture instead because it's looking more easier. Again, this is oversimplified, right? So the return is kind of like the ID, the identity. And these things, when you do the fat map or do the binding, it have a left associative. Okay, but so somehow it's have an associative. So this may be actually the whole things that implemented maybe is the endo functor. So we already have the endo functor, which is have the ID, have the associative. This is the category of maybe, right? This is a maybe of some type, maybe of some type, maybe of some types. Then the whole things, this is the idea of monad, right? So how Rust use the ADT, algebraic data type, to create an option. Option is the same thing as maybe in Haskell, right? Behavior that like a monad, but not really a monad. That's it all. Because maybe it's gonna be not things, or maybe gonna be just a talk for me. Just that.
All right, big round of applause for people of Avantis.
Okay, hello, thank you. Yeah, so my title is very clickbaity. It just sounded better than carefully replacing Java with OpenAPI and Rust when it did to have more impact. So I'm Alex. I'm based in Singapore, but I'm in town this week and get to talk to you here. I work at a company called BigPay, and I'm going to talk about our transition to Rust, which is ongoing. So throughout the talk, I'll give you some background on what BigPay does, what our tech stack looks like, why it looks that way, and then how we're transitioning to Rust, what that looks like, and then talk a bit about OpenAPI, which is one of the tools we're using to aid in this transition. So what is BigPay? We're an e-wallet app. Comes with a card, and then you get a bunch of financial services. So, sign up, do your eKYC. We'll send you a physical Visa card. You get virtual cards. You can remit money and so on. So basically a challenger bank. We're in the Singapore and Malaysia markets right now, though we're expanding in the region. We'll be in Thailand soon. We have an office here. That's why I'm here. A bunch of good engineers here. And we're looking at other countries as well, Indonesia, Philippines, and so on. So hopefully you'll hear more from us soon. And we're not that big. We have about 200 employees, a little bit over, and about 50 of those make up our tech team. And that's across everything in tech. So backend, mobile, infrastructure. So I think we punch above our weight. But yeah, this talk will be, in that context. We're not a huge company. We have limited resources, and we're still trying to move to Rust. And so a lot of what I talk about, is applicable to that. And actually looking forward to hearing the talk about Agoda moving to Rust and how that contrasts with what we've done. So some background on our tech stack. So the original BigPay was built by a team of contractors. And they were, building a system that was rapidly changing. We were a new startup. They had to ship or we would die, as all startups do. So that was the priority. A clean system was not the priority because we needed products for customers to use. And eventually the tech was brought in-house. And now, we're almost all engineers work for BigPay. And what the tech stack looked like when it was sort of handed over was about 40 to 50-ish Java Spring Boot services that communicate via REST and Kafka. And there's a lot of tech debt. Many of the original devs that we had working for us from the contracting company had moved on, some stayed, but we lost a lot of that institutional knowledge about how much of the system worked. Everything was in Spring Boot. Spring Boot has a lot of magic, a lot of batteries included. Not to knock it, I used to work in Rails, so I'm a fan of frameworks, but yeah, they can also bite you in the foot. And we also just didn't really have kind of the institutional will to just embrace Spring Boot. So we just needed to figure out a way to kind of manage it. And we had a bunch of other problems, like everything's written in Java. We have no idea what fields are null. And still many data types I couldn't tell you. And we're still discovering what can be null. There's a lot of logic in SQL triggers. Services are slow to start. Tests were becoming very flaky. There's a lot of integration tests built with Spring Boot. And they just, started rotting away. You would make a change and then 500 tests would fail in like a later test. And you realize the validation test was spinning up Kafka and pulling messages off. And it was a little bit scary to change things. And a lot of the domain boundaries, over time didn't make sense. The services were probably much bigger than they needed to be. And as the business had changed, a lot of those service boundaries just didn't make sense anymore. So the path forward we kind of, over time decided on was, a few principles. So if you have to touch an old service, like please write the code in Kotlin. It's not always possible because of some intricacies with Spring Boot, but we try to do that. And then in our new services that were not Spring Boot, we wanted to go no heavy frameworks, prefer libraries over frameworks, no heavy ORMs that surprisingly cache things or do things in an unperformant way. And, not using heavy frameworks and ORMs make it easier to read the code, figure out what's going on, and so on. And we decided that Rust was going to be our language of choice. I'm not going to go through all of the benefits of Rust. You guys are all here. I think we all agree that it's pretty cool. But we did have some trials where we rewrote a service in Go and one in Rust at the same time, and ended up just as a company deciding that Rust was the way forward. And when we had the opportunity to rewrite old services, we would choose Rust. So how did we go about that? So spinning up new services, very straightforward, right? But the rewriting part is tricky, especially because, again, these old legacy services were not well tested, and we don't want to touch them. As much as possible, we don't want to touch them. Changing the code is scary. It broke things in ways that were surprising. We would have occasional production incidents because of very innocent looking changes, and no one understood what the deeper parts of some of our oldest services. So we came up with a sort of technique that we did fairly successfully multiple times, and we're still doing. And it's a classic way of dealing with legacy code that's not well tested. You find sort of the edges of your system where you can stick a shim in there and isolate the old part of your system, write tests, and make changes at the boundaries, and eventually redirect things. So what that looked like for us in our backend services was spinning up proxy services and just sticking them in front of our old services and redirecting all of our API calls from the rest of the system to go through these proxy services. And then once we had the proxy working, we would rewrite the logic in that service in Rust, and then using feature flags or configuration, we would slowly migrate the traffic over. So in the best case, it would be, you could isolate a single user's traffic and use feature flags to just move them over, and we could gradually test it. Sometimes it's big bang. It depends on what the service does, but that's worked quite well. However, there are a lot of challenges doing things this way. So the endpoints are, unsurprisingly, not well documented. We have handwritten clients in a lot of the other older services. So for instance, if we had a service that tracks the limits of your transactions, and then maybe 8 to 10 other services were calling this service, and they each had their own implementation, the API client in the code base. And so that is obviously hard to work with. Some of them varied in some surprise ways. And again, not sure what can be null and so on. And it was very tedious to have to write 2 clients, maintain 2 code bases in Rust and Kotlin. And so we wanted a better way, right? So this is where OpenAPI comes in. So if you don't know what OpenAPI is, I'll do a quick introduction. So it's basically a data structure for describing REST APIs. So you can see here, this is like an example file. You can describe everything about it, right? Like, here you can define your server endpoints and so on. You can define every path, the method types, you can document it, record the responses, again, more documentation, content types, and then return types. So a well-documented API, OpenAPI, will include every single path, all of the request types, query parameters, response types. It'll describe the authorization, and it can be serialized in YAML or JSON, though we've used YAML and we hand edit the files, and I'll get into that in a bit. But yeah, so another fair question would be like, why not just use something like gRPC and use protobufs, which I honestly would do if we were starting from scratch. But again, we're trying to not touch these legacy services at all, just as much as possible. And we had some previous attempts at documenting APIs with OpenAPI. I think that's quite common. A lot of people ambitiously will try to document their APIs. They'll maybe spin up markdown books with the documentation. You can generate documentation using the OpenAPI files, but they fall out of date. And so that's what happened, but it was a nice starting point. Yeah, so in this quest to rewrite these services and so on, how does OpenAPI help? Well, if we think, what are the goals we were trying to accomplish? One was to make the client and server creation much less tedious, right? Like, we don't want to maintain 2 clients across 2 different programming languages. We don't want to have to constantly be writing these API endpoints in code. They'll be implemented in slightly different ways by different people and so on, not consistent. And then, we'll have other problems like library versions will get out of sync. I might write a server in Axum. Someone else will use Warp. Unless you're very disciplined, like, these things happen, right? And we also want things to be documented. We don't want to continue moving forward and still end up with a system that we don't understand. There's not good documentation. And so our solution was, generate our code using our documentation, which means generate code from the OpenAPI file. And of course, this is being done already, right? Like, there's a very active and large GitHub project called OpenAPI Generator, and it does that. It generates clients, servers, and documentations using your OpenAPI files. But there's a few problems. Like, I had some previous experience with it, generating TypeScript clients. There's a lot of edge cases. There was, the project is very large, so there's multiple different like sub-projects of how you can generate, for instance, a TypeScript client using various libraries and so on. And they all acted differently. They sometimes generated code that wouldn't compile. And I just didn't feel like it was the most stable way to do things. And it's also a Java project. And we're, at this point, very into Rust, right? So we want to avoid more Java. So, of course, we wrote our own. And so what does this look like? So it's written in Rust, obviously. That's why we're here. It generates clients and data transfer types for Kotlin and Rust. API request and response types. It generates Rust server stubs. It integrates with our internal authorization system. And it has support for some of our internal libraries. And one of the key benefits of writing this ourselves and getting it out quickly was allowing it to integrate with our internal auth. So rather than hacking on an existing project and trying to make things work, I actually think this was probably a quicker and more stable route. And so what does this look like? So for an example, I'll talk about one of the server stubs. So when we have an OpenAPI file that has, an endpoint like this one. So it's a get cards endpoint. We give it a operation ID, some documentation. We describe what the authorization is. This is a custom extension we wrote that fits within our auth system. And then we describe the response. And you can see here, it should return a 200, and it's a JSON response type, and it returns a card response. And then this is referencing something, further down in the file, a schema where you can essentially define what your data type looks like, list the fields, list the type, say if it's optional, and so on. And then this is what it actually looks like when you're implementing this endpoint in our services. So this here, this trait called card service API is generated by our code, and you implement it on some struct in your service. And then every function maps to one of the requests that's defined in your OpenAPI file. So here, we're implementing the card service API for some struct called API. And we have a function, get cards for user, maps directly to the operation ID. And it takes as an argument, in this case, just the user ID, which it's being passed because we define that the auth role for this endpoint is user. And we have other auth roles like system auth roles and more granular ones. And depending on what sort of auth they are, it'll either pass a user ID or not pass anything and just make sure that the request is valid for that auth role. And then it returns a get cards for user response, which is defined here. And so this maps one-to-one. And this type is shared between both the server stubs and the client that we generate. And this one's pretty straightforward. We, pass the user ID to some service, get the response, and then build the HTTP response and pass it on. So how do we use this generated code in our code base? So we have a mono repo, which makes it a bit easier. We have separate crates that hold the request types and response, the clients and the servers. And our code generation automatically looks for OpenAPI files in our services, generates the code, and then sticks them in these crates. So, this is an example of a cargo.toml file. You see, it's just like referencing the different libraries where we generate code relative to the project. And so this is, and now I'll dive into a little bit about how we actually go about generating that code. So if you've never played around with it, Cargo has a build script feature where you have a build.rf file in your project. And what Cargo will do is compile that build script and execute it before compiling the rest of the package. So you could do, well, I guess anything you want in there. And what we have here is the example of the build script in our server stub project. So here you can see we're importing our library, OpenAPI to Rust, and the function generate server. Here, this is pretty straightforward, right? We have an out directory. This environment variable is set by Cargo. We call the function to build the servers. This will output a string. We write it to the generated .rs file inside the output directory, and then save it. And then when the package compiles, it'll compile that code as well, and it'll be available for use in that project. So what is that generate server function actually doing? Like I said, we're in a mono repo. So the first thing it'll do is look through the code base, just looking for OpenAPI files, right? We know we put them in the same place for every project that has it. So it'll collect those up. We use a crate called OpenAPI that has just the data type for OpenAPI, and we'll parse the files into that data type, and then we merge them all together into a single giant OpenAPI structure. We have to do a little bit of modifying so we don't get name clashes and that sort of thing, but it generates good names. So then we take this OpenAPI data structure and we convert it into a token stream, mostly using the quote macro. So what is the quote macro? So the quote macro is a nifty little library that allows you to write what looks like Rust code, but is actually generating a token stream. So this is data. This is not code, even though your IDE makes it look like code, which is the benefit of having it. So this is an example of us extracting the user ID from a function. So yeah, so we call some helper function, and then if it's there, we return it or we return an error. And once we have this whole token string, you can imagine we're calling this a lot, like for many different things. That's how we generate the traits, how we generate the clients. And it looks like we're just writing code for them. Then we convert it to a stream, and then we write it to the generated RS file that you saw. Then a fair question to ask is like, why are you doing this token stream stuff? Why not just do string concatenation, right? Well, we do that for our Kotlin clients. I put two examples here. So on the left, you can see this is where we're defining a client for Kotlin. And on the right, this is how we're defining a client for Rust. I think it's much nicer to write the code using the macro system, though you don't have to. But having the syntax highlighting, having it look like code that you would write makes it much easier to think about. So when you're modifying the code generation, I think it's a bit easier, though we wouldn't necessarily have to do it this way. And obviously, we're not for Kotlin. And there's a couple other cool things that it does. Because we're generating server stubs, we're able to keep a unified web framework behind the scenes. So for instance, we recently swapped our framework from Warp to Axum, or I was hoping it would be, I don't think it was actually merged. It was should be merged soon, but we're we're almost there, and we can do it almost completely transparently because it's all hidden away behind the server traits. We also have some tests to validate that our code generation is working correctly. Mika, I hope I'm describing this correctly. And we spin up a server, we create an HTTP request, and we feed it to the server and validate that we're receiving all the data that we expect. That way, if we mess something up in the code generation and we forget to, for instance, pass a query parameter or headers, then we should be able to catch that with these tests. And we also have support for internal libraries, like our internal money library. So we can a schema that we define in OpenAPI as, this field is the BP money type, and then it will be parsed and validated and available in those client and server stubs. Cool. And so now, isolating and rewriting these services is much, much easier and much less tedious. And the general flow is you document the existing API. That's the most important part. And then you generate the stubs in client. And then the proxy service, so this one here, is really just stringing these two things together. So if you remember, the request and response types are shared between the client and the server stubs. So the initial version of these proxy services literally is just you're implementing the server stub and then immediately calling the client, which is pointing to the old service. And then over time, we can implement the logic in those endpoints and migrate users over. But all the tedious work is done. And since we're generating clients in two services, or in two languages, excuse me, then we just have one pass it updating all these other systems with the handwritten clients and saying, hey, just import the client from the internal library, and then we can get it all on the same code base. And then if, for instance, we launch this proxy service and then we need to make updates to the API, it's just a matter of updating the OpenAPI file for the service. You compile the rest of the services and then you'll get compiler errors if there's a breaking change in the API or something like that. And it's much, much easier to catch those things now. And then, rewrite the logic and migrate. And so it's a much simpler way to do that now. And so this is the current state of us trying to kill Java. Obviously, we're not completely successful yet. I think we have around 35 Rust services, still about 45 Java Spring Boot services. So still a long ways to go. But some benefits beyond a better programming language and better developer tooling and so on is much better resource consumption. So seeing much better startup time. So one of our gripes with our old Java services is they would take forever to start, like 15 seconds until a health check is responding 200. And now with the Rust services, we're seeing, what looks instant to a human, which is awesome. And then the memory usage is way down. This afternoon, I was looking at the memory limits we set on our rods, and our Java services, almost all the services, we set a limit of 2.5 gigs on the low end and 4.5 gigs on the high end. And all of our Rust services have a memory limit of 128 megabytes. We never even get close to it. It's pretty sweet. And that's it. And the battle continues. We're still trying to kill Java with some success. And that's all I got. Thank you.
Thank you, Alex. Thank Thank you, Alex. I think we have time for questions. Any questions?
So we can see that you have some improvements in the startup time and in memory terms. So what about the implementing new business feature in Rust? Is it about the timing of the development? Is it was decreased? We have some statistics about this.
I don't think I have a great statistic on implementing new business features. I mean, I only have anecdotes so far, but I feel like it's way more maintainable. Again, because the Rust types are well defined. You mark things as null. You mark things that the error handling is much better. So we do find that going. Though this is a hunch, should get some numbers on that. But yeah, I mean, I think it's much better. And I'll find some data to prove that one of these days.
Cool.
Rock, paper, scissors.
Thank you for your talk. One small question from my side. You mentioned that your heap size is 128 megabytes, but you know how it often works in the enterprise when you end up with the JSONs, which like 5 megabytes or something like that. I just wonder, did you consider that problem? What your payload at the peak hours might be bigger than your heap size, even though you are quite efficient by handling it?
Yeah, I mean, we haven't run into that problem at all. I mean, almost always our payloads are quite small. I mean, I think we're just over provisioned in general, so we're not even getting close. And we're big, but not so big that that it's too expensive to like over provision. Like
I don't have.
I just have basically a question for the library itself, because most of the framework that I use actually the OpenAPI JSON or whatever it creates. It also comes normally packed with a Swagger, a way to actually test the API with integration testing right away. Are you planning to kind of expand it in that direction, or is it maybe just this is it first and then we'll do something else?
Yeah, I mean, we haven't looked super closely at auto-generating integration tests that are actually testing business logic, because it's actually quite tough to kind of auto-generate data that makes sense within the system. Now, we do have an integration test suite written in Rust, and we use the clients extensively. But yeah, we haven't put time into auto-generating the tests, basically. And I'm not 100% sure it would be possible to make good good auto-generated data, unless maybe we extended the OpenAPI files to include hints on what sorts of data beyond just types. So I don't know.
All right, big round of applause for Alex here.
Okay, guys. Hi, everyone. Thank you for making it here today. Sadly, I think we don't have already like half of the seats. So, but thank you for making it to the latest talk of the night. So my name is Eugene. I'm on the left, and my colleague is also Eugene. He's on the right. This is the guy. So basically, we are working on the same team in Agoda, and we are doing some kind of techie stuff. So our main project is the metric time series database, which is internal and is sourcing the most of the data sources. Sorry, the most of the dashboard in Agoda. And that's why this is one of the reasons why we decided to choose Rust. And basically, our talk will consist of two parts. First one is the simple part, which I will tell, and the second part is the interesting part, where we'll tell a bit about tooling. This is another Eugene will tell about. So let's start. I would want to start with the survivorship bias. So there are multiple interpretations of this thing, actually, but our one is following. For example, imagine you crashed your plane and you made it on the deserted island. You have no food, you have no water, the sharks are scooping around, and you did some actions, and now you're sitting in the middle of the TV show and you're telling the person, like interviewer, how you made it there. So, but on the other hand, if the same person will hit the plane on the same deserted island and he will follow exactly the same suggestions what you gave it to him, like he may not survive it. So this is our story. We are here not as an experts, but as a guys who actually made it. So basically, yeah, we are here. If you have some rotten tomatoes, throw it around, and let us know if you are doing something terribly wrong. Again, why we're here? First of all, we are writing in Rust about a year or a bit less. About 6 months in production, or like 7 months. We've written about 30,000 lines of code, which we consider as a medium-sized application. And in fact, we didn't really even throw it away. Like we made it to the release, and it's something people are actually using, and people are kind of okay with. People are saying it's quite fast. So, yep. And what did we exactly build? Like our new project is a brand new internal distributed log aggregation platform. So obviously one of the requirements is we need to consume hundreds of thousands of events per second, like which are basically the logs. We consume it from Kafka, et cetera, et cetera. We have a lot of them since we have a lot of logs. We are kind of big company, right? So after we consumed it, we did some magic, some buffering, and we need to actually save this data on disk. We need to do it effectively. That means we have a lot of I/O as well as disk as network. And next, we need to query it somehow because people want to see the dashboards. People want to debug their production issues with these logs. And that's how we need to provide them access. That means what we need to orchestrate MapReduce style queries to whatever we aggregated. And again, why did we choose Rust? Well, one of the reasons is because we can, I guess. The second is like our current solution is using the number of cores, which is measured in thousands. Like we literally have kind of big machines of 1 terabyte of heap for it. And then people say what we use 128 megabytes for rare applications. It's quite fascinating. Yeah, and the ultimate goal for our new service is to use less resources and be faster. That's why we, in the end, decided to use Rust. So what are we not going to cover in this talk? We are not going to cover the Rust basics. Basically, it's Rust conference. If you ended up here, we expect you know something about Rust. Also, we are not going to sell you the Rust. Like we have also a lot of people, including Idan, who sold you Rust already.
And we are not also going to say what Rust is better than Java or is it worse. Yeah, don't look at it. So another thing is what is covered. Like I will tell and Eugene will tell how do we actually run the project, how do we deploy, test, and develop medium-sized project, how do we debug profile production issues, spoiler, hard, and challenges we faced during the Rust adoption. What are your thoughts then? You see the iceberg on the presentation. Yeah, basically on the top, the expectation, what you've been sold, what helpful compiler, like it helps you, it guides you, it tells you what you're doing wrong, it tells you exactly what do you need to fix to be successful and to get a lot of money. Also, it's performant. It doesn't have GC, like considering when you're coming from Java, it's like a big deal, right? Because if you have a lot of heap, you have a lot of memory, you have a lot of allocations, you have a lot of GC, and your money goes down the drain. Also, instant application starts when you're coming from things like Spring Boot and your application takes like 10 or 20 seconds to start. In Rust, it doesn't exist. And memory consumption as well. If you in Java, if you have things like boxing, you have a lot of different things where you can spend your memory, and you think it's kind of okay because you're used to it. Then you come to Rust, you see what you actually can live without it, and it's kind of interesting. But there is another layer, which is reality. No GC is not coming without any cost. First of all, it's a concept of ownership. With concept of ownership, you have a borrow checker, and you have lifetimes. Like only these three things can make a developer who is coming from from Java to cry. And it's kind of at the same time, it feels like what the compiler tries to break your fingers. But in the end, this is the things what makes Rust great, right? There are other things which I marked as yellow, which is async. If you're writing async code, like it's another level of rustiness, which means whatever you knew before, it's kind of next level. There are also macros, which I personally, after six or 7 months, don't know. And I don't know how to read them. I don't know how to write them. Also, there are unsafe code, which basically tells, like, yeah, Rust compiler, yeah, you're great. You're telling me what to do, but I don't know. But I don't want you to tell me any suggestions. I will just do a plain old C++ code with sig faults, sig name, pick your poison, etc., etc. So we are not going to go there today. Now, after all this like inspiring speech, you're thinking yourself how to deliver a project in Rust. First of all, you need to read some books. You need to watch some talks. If you're going to skip this step, you probably fail because it's not something you can take from the Stack Overflow and it will work from you. Like talking from my experience, it was quite miserable a couple of first weeks. After that, you're choosing the IDE. You decide on libraries, you decide on configuration, you figure out how to organize your code, you cover it with tests, you release and ship it, profit. So the IDE, there are a lot of talks which IDE you should use. Some people use Visual Studio, some people use IntelliJ IDEA, some people use C-Line, some people are happy with whatever you can code in, like Nano, Sublime, Atom, etc., etc. In our case, we picked IntelliJ IDEA because we are basically the Java guys, and we are people of habit, so we decided to not go against it, and we just plugged in the plugin of Rust, and we are happy with it. Some people say that C-Line gives you a better experience of debugging low-level stuff, like, I don't know, some low-level stuff, basically. And I don't remember exactly why didn't we use it. But in the end, we are using the IntelliJ IDEA. The reason why you can use Visual Studio, the biggest one, is the integration with the dev containers. Dev containers allows you to not pollute your system with a lot of different combinations of software you need to install. For example, if you're cross-language developer, if you have a zoo of different technologies, you write in Go, in Java, in Rust, like Visual Studio probably is your choice. So let's quickly go through the dependencies which we are working with. First of all, it's obviously Tokyo because it's the biggest Rust async runtime. Next, it's an Axum. Also, it's a server for JSON. Also, have a look on the stars from GitHub. Like these guys are quite popular. Another thing is requests for making HTTP calls, SQLX for interacting with the database. Some more dependencies because we are working with the Kafka. We picked the RD Kafka, which was the fastest, I think, from the benchmarks. We picked Rayon because we are doing a lot of different computations with the file systems, and Tokyo is not really great at it. We're also using the hash brown, which is implementation of the hash table, which is pretty good in terms of comparison with the standard library hash map, like 3 times faster on average. And we are also using dash map, which is also fastest concurrent hash map analog to the Java version which we have. So now let's have a look on the project structure in Java and Rust project. In Java, it's quite simple. You have model 1, model 2. In each package, you have main package, test package. So you have like differentiated code. You have a production code in one folder. You have test folder in the different folder. Sorry, test code in a different folder. And you have your POM XML, Gradle, build, SBT, and whatever. In Rust project, it's almost the same. You have cargo one love, and we also work in the repository with multiple models because we want to share some functionality between the models. And Rust has pretty flexible model of sharing packages. For example, in mod.rs, by default, you can specify whatever code you share between the packages, what is actually meant to be private. And you can share the code in the same manner between the models, and you can forbid of sharing these things. So this is quite flexible, and this is really convenient to use. Configuration. So the TOML is de facto, as far as I understand, TOML is de facto standard of the configuration for Rust. You can also put your configs into YAML and JSON, but for us, it didn't really work because it doesn't support inheritance. It works pretty badly with environment variables. And it's kind of inconvenient to have a lot of the same configurations, which are different by some like little number of properties. That's why we are actually not using them. And instead, we went with something which we used to from working with Java, with the Hokon library. So with the Hokon, you can do something like that. For example, if you have 5 to 6 data centers, in each data center you have 3 different configs. You have like something common, for example, S3 dependency, database dependency, I don't know, Vault dependency, whatever else, Zookeeper dependency. And you can just substitute whatever you want at like some configuration properties. And in case, for example, if you're moving the Vault from HTTP to HTTPS, you will need to change only one file instead of changing like all of your 30 files. Now let's have a look on the code architecture in Java. Like have a look as well on the enterprise namings, like business manager, factory providers, etc., something we all love. And this is plain old Java, like nothing to talk about it here. The architecture from the tutorials on the GitHub, like just place everything into one main file, and it will be a success. It will be 500 lines of code, but nobody cares. So yeah, this is how you basically start developing in Rust. Okay, let's check the audience. Could you please raise your hands if you have main file with the all functionality of the code? Come on, it's okay. Right. But in fact, you don't really want to have something like that here. So you decide to emulate the same thing in Rust. So you have a structure which called business manager. You put the dependency inside of it, and then you create, like, then you emulate the constructor. You have a new. So, and you're passing dependencies here. So, like, sounds like something that could work, right? Well, kind of. But we have this guy who is suspicious, and he says, well, the same structure can be used somewhere else. What it means, for example, if you have the database pool and you don't really want to create different database pool instance just because you cannot pass it properly. So and it goes the same for every dependency. For example, if you have a singleton in Java, it meant to be a single instance, so you don't really want to create it for any dependency that's a different instance of the singleton. So it's fixed kind of easy. You just put the lifetime. So basically, the lifetime means what this is the reference, and this -a is a lifetime. It means what the reference of something you put inside of the class or the structure will live the same amount of time or longer than the structure you're passing it from. So yeah, we have the suspicious guy again. So the problem is how to test this code. In Java, you just create an interface and you're mocking it and you're doing whatever stuff you want in the tests. Well, in Rust, we can do the same thing. We just use the library which called automock. And you create an interface, you create the implementation of interface, and then you call it like that. You just say what I can, instead of passing this like specific structure, you can say what I want, what I will pass some implementation of the trait. And this trait can do some stuff. That's basically just one DIN keyword. Okay, so we settled the simple stuff. Now let's consider what we are going to do some background computations. That's obviously not the best way to do it, just a triable example. For example, we are going to call the database like every 10 seconds in a separate thread. Will this compile? No. First of all, compiler is pretty carefully says to us what dependency, what you're trying to share, is not actually safe to share. For that, we say compiler, no, in fact, it's actually safe to share. You just add the sync and send marker. In this specific case, sync is not actually required, but after writing 6 or 4 months async code, you just put these things together wherever the compiler is actually having something to say to you, just to keep safe. And the compiler is still not happy. Now it says what he actually wants, the static lifetime instead of our specific lifetime. So now we are kind of really scared. We don't know what to do. So what can we actually do about it? Yeah, basically you have the atomic reference counter, which is you don't have a GC, you're going to emulate the GC, and now you're creating the atomic reference counter wrapper around the object, which you don't have a strict lifetime of. And now every time you're going to pass this object somewhere, you're going to increment the amount of references. When the object with the reference goes out of the scope, you decrement the number of references, and then the number of references goes up to 0. You deallocate the object where you have the wrapper of. Yeah, everybody is happy. That thing works. And this is something actually a lot of people go with production. We don't have trouble with, perfectly fine. But we went further. In our case, I already told, what we are Java guys or Scala guys or JVM guys, and we are kind of having a lot of different singletons, right? What is singleton? Singleton is effectively the instance of something which you create once and forget about it forever. Static lifetime is effectively the same thing. You just initialize and forget it. You don't ever drop it. You don't need to clone it. And it's applicable for permanent projects. So that's why we actually do that instead of arcs. All of our dependencies, which can be static, made static for the sake of happiness of us and for the sake of easiness of development. And this thing also works. You just say what this self, which I'm calling the method of the start doing stuff, is static, and your thread's also okay because whatever you pass, whatever thing you have inside of this class is also static. Profit. But if you try to declare something static, you basically know what it has some issues. If you try to declare a static hash map, it will tell you what it will not work because the functionality of creating the hash map is not static. So and even if you cannot even create the hash map, like what we are going to tell about the custom structures with a custom business logic. For that, we are using the static init library, and it actually quite flexible. It can allow you to create your dependencies in the order you want. For example, you can create it lazily. You can create it like lazily upon the first access. You can create it whenever your application started. But this is how we do our stuff. Also, basically, if you want to have your code async, you just slap async. We already seen the example in the previous presentation. But if you just add the async here, it will not work. Just because the Rust is actually not supporting it for now. I hope it will, because this exact thing sounds a bit suspicious. What it actually asks you to use some external crate to support the async and traits. And you just follow the recommendation, you slap the annotation and slap dependency on your trait and your implementation. And this is effectively how you write asynchronous traits. Now about async. We are not going to go into the async because, as I said, asynchronous Rust is entirely different Rust. And I highly recommend everyone, if you didn't actually read this article yet, like this is the guy who is much more competent than me in Rust. And he actually wrote why Rust async is hard. And like from my experience, when we tried to create the async Rust application, first of all, we've written it like in one main file. It was 200 lines of code, 300 lines of code. And I've done it, I think, in 3 or 4 hours. And then I obviously, as a good team member, I created a task like refactor this on the next sprint. And then I spent 2 weeks doing that just because compiler wasn't happy with whatever I was doing. And I wouldn't succeed without Evgeniy also. And the final thing, now imagine what you succeeded with Rust. You want to release it, and you want to set up a continuous integration for it. As you see from the logo, we are using the GitLab YAML for that purpose. And as a first thing, for the sake of cleanness of the project, we highly recommend you to put this thing into the main file, which will deny all warnings which you will have. It will make your code base much cleaner, and that will also save you some nerves because you forgot to use some variable and you used a different variable because of it. Or you just forgot to remove unused dependency, which doesn't really matter, but makes to keep your code cleaner. Another thing is like the good code base is a formatted code base, so you just install Rust FMT and check what your code base is always formatted. Another thing is like I hope you already covered your code base with tests, memory tests, performance tests, unit tests, integrations tests, functional tests, etc., etc. And another thing which is quite healthy for the big project to do is to have a change log, just to make sure what between releases you can forward back to something and figure out what was there, what is actually deployed on production. So for that purpose, we have cargo release, which actually like in the latest release broke the backward compatibility and it doesn't work anymore because they removed a couple of annotations, but it doesn't matter, it's still good. Yeah, and after you actually released it, you want to ship it somehow to production. And comparing to Java, Java has a slogan, write once, run everywhere, or test everywhere. Rust is not like that. Rust is not portable. And to properly ship Rust, like for easiness, you should wrap it into the Docker or into the WASM. We just wrap it into the Docker and put it into the Kubernetes. Like Kubernetes is optional. You can put it wherever you want. In our case, some applications, some stateful applications are also deployed directly on VMs. And let's get back to the iceberg again. So as you see, we still have some space here. And basically, there is another layer, which is hell, which is Evgeniy going to talk about. But basically, it's a tooling, it's a heap fragmentation, it's seek faults, it's seek eels. I don't even know how many people know what seek eel is. I didn't. And other low-level funny Unix problems. So, word to you, Evgeniy.
Thank you.
Thank you. So let's start from the good stuff. During the project development, you will have to choose between different algorithms or data structures. And in order to make a proper choice, you have to have some numbers using basically benchmarking. So in our case, it was concurrent data structure for string and turner. And we tried the following tools in order to make our choice. So first of all was basically libtest, which is built in unit testing and benchmarking framework. However, benchmarking annotation is available only on stable Rust. And our project is strictly use stable Rust toolchain. The next one was YAI. This is a precise tool for precise single-shot measurements, and it's very good for, to run in your CI. And the last one is a solid statistic-driven micro-benchmarking tool, which is Criterion. So let's review them closely. As I mentioned, YAI is very good for CI environments since it's produce non-flaky results, and you definitely don't want that your performance test produce flaky results in order to waste time to basically find it hotspots. And YAI achieve it by using Wiles. Wiles is the binary instrumentation framework, so it's produce as I mentioned, quite precise result, but at the same time, it's slow down your code significantly. However, it's still faster than statistical driven approach. The biggest problem of YAI, it doesn't have any nice HTML reports. However, as I mentioned, since we use it only for performance regression tests, for us it's pretty fine since YAI provides simple access to CPU count, CPU hits, and RAM access. So with these numbers, you can build pretty easy regression performance tests. And finally, Criterion. So as I mentioned, it's produced quite good reports with graphs, and it's also support async functions, which is important if your project rely on async stuff. However, since statistical nature of this benchmarking tool, it's have a lot of run, and this run will give you very flaky results in CI environment. So let's review a little bit the code. In Criterion, you can very easily set up your benchmark tests. Just specify your function and specify input parameters in order to prevent Rust to you will get pretty nice picture. At this step, you probably doesn't say you a lot since it's very internal stuff of our project, but in the end, our custom string internal is faster over dash map since we apply a lot of workarounds, which is strictly applicable to our use case, and probably no one outside of the world will be applicable. So yeah, once you successfully build your project, deploy it in production, one day you might face some unexpected behavior of your system, and you might want to start investigate what happened with your system. In JVM world, you basically can just send a circuit signal to your Java process and get pretty nice thread dump, which will help you to investigate what is blocked, what is not blocked, and get a lot of insight what is happening. In Rust, it can be achieved as well, and it's achieved pretty easily with stack crate. This crate uses ptrace system call, which basically do all the job. However, during using this crate, you should remember that if you run in the Docker or any other containerized environment, calling ptrace require root admin permission. So you no need to forget to enable this Docker capability. And second one, it's related to Linux. You cannot just call ptrace from the same process. You should to have some child process, which basically will call ptrace system call on the parent process, and then basically you will get your thread dump.
And the last, what you need to remember, if you have integration with some libraries and these libraries has some side effects to your standard output stream, then you will fail as well. So you need to be sure that the standard output stream in the child process is clean, since RStack uses standard output stream as a pipe to transfer thread dumps from the basically child to the parent, and then in the parent process you basically can print it, log it, or up to you. So once you follow these simple steps, then you have pretty detailed stack dump that you can use in your investigation. Another problem that you may face during your project development and maintenance is deadlocks. Despite there are not so much deadlocks in Rust because of compiler, there are still possible some of them. And we face first our deadlock when we upgrade DashMap. The previous version of DashMap uses standard basically Rust mutexes, and with comparison in async code, it's pretty dangerous stuff. So DashMap basically fixed this stuff by switching to parking lot crate, which provide a completely separate implementation of mutexes, and it's have a lot of killer features. Like, first of all, in case of deadlocks, your thread will just panic, and it's very big benefit because in this case you no need to just take thread dump and understand what is happened there and where it's stuck. Another one big benefit is all synchronization primitives from this library can be used as static variables, since this library doesn't have any kind like heavy state in the constructor, so constructor can be just constant and there are no destructors. So they achieve it by just wrapping atomic variables and do basically whole mutex magic. And the last one feature that save our project is basically reentrant logs. Since we have a lot of async functions, it's pretty convenient when your function can have reentrances, since during execution of async tasks, you don't control on which worker threads it will be executed. So basically, yeah, that's all. So once you fight with this topic, another topic that you might remember is binary incompatibility between AMD and Intel. We was never aware that there are such incompatibility, and I'm not sure how many percentage of people are aware that we have one. Oh, nice one. So first CGL crash for us was very, very kind like confusing, because first of all, this CGL crash is not panic, and you will not have it in your logs. It will be in the message basically. So you need to understand. Don't forget to check kernel logs. And second one, once you will get this stack trace, you need to don't forget that by default you will not have any core dump. So first of all, you need to enable core dump in your Docker image, and then once you get core dump, you can run GDB and find some instruction, and then open source code, and then you will see that okay, everything is fine. It's usual code. What can go wrong? So for us, it was pretty new experience, and we eventually found, after digging in assembler, that some instruction, as you can see, insert Q, which do some permutation in CMD registers, this instruction only available in AMD. And in our case, our CI is using AMD machines, but our production is using Intel. So that's why we got CGL crash. So yeah, this SSI4 instruction set contains 2 instructions, but they are very tricky and very easily to forget that, okay, I need to specify my CPU target pretty closely to production. But yeah, please don't forget it. So when you fix all these issues, another problem that you may face is performance. And to solve your performance issues, you might thinking to start profiling your applications. In JVM ecosystem, profiling is quite simple, I would say, because it doesn't matter whatever profiler you will choose, anyone will give you all-in-one CPU profiling and memory profiling. So you probably will solve your issue pretty quickly. However, unfortunately, Rust rely on native profiling tools with some pros and cons that will be described right now. So first, very famous profiling tool, which I already mentioned we use in our performance regression test, it's Valgrind. However, Valgrind is good for tests, but you probably will never run it on your production system since it will slow down your application by 20-30 times because it just apply binary instrumentation. Then there are, of course, some optimization with dynamic recompilation by virtual machine. However, it's still significantly slower. That basically, in case of real production, just unusable for the end users. So we switch the next one, which is Gemalog. Gemalog, it's not just profiler, it's a pretty good scalable memory allocator with heap profiling capabilities. And it's used by Facebook. So we kind of like have some promises on that, but I will describe what issues we faced with that one. Once we faced issues with Gemalog, we tried byte-honed one. It's very promising memory profiler, which is written in Rust. So there are least problems that you will have, except, as Eugen already mentioned, we have very huge heap dumps, 32 gigabytes, 64, and up to 1 terabyte. So unfortunately, this tool right now has issues with such big heaps. And the last one, which is work for us, however, it also have some inconveniences, is HeapTrack. It's just generic memory profiler for Linux environment, but it also have pretty nice GUI that almost can be comparable what you can see in any Java profiler. So let's review. So Gemalog. First of all, what we face in our project is heap fragmentation. How we spot it? Basically, shared memory not increased, our monitoring matrix is fine, and then suddenly application is crashed. So after, again, checking this basically metrics only available in Linux kernel log. So as we checked, we see that, okay, it's out of memory. So we start dig down and try to find, okay, how it's possible that memory not increase, but application still fails. And then we see that a number of kernel pages that are allocated by system libc allocator is just increasing. So we try to Google, and then first one that we faced is basically memory allocator that Facebook use in their production system. So how it's reduce heap fragmentation? Each allocation of each small object can basically take a lot of if there are a lot of allocations in the one page, then allocator can take another page and then allocate one. But then once your allocation size is increased even for 1 byte, then the next one block that will be used for your allocation still cannot fit in the old page, and then allocator will request the next kernel page, and that's how you basically will end up with out of memory. So Gemalog is solved completely by segregation or allocation by small, quite precise allocation sizes, like 4 bytes, 8 bytes, and blah, blah, blah. There are a lot of one. Another big pros of Gemalog in comparison what the default Linux allocator provide you, it's statistics. Since you probably want to have much more than just number of kernel pages that allocated to your application, that's where Gemalog can show you how many allocations of each size happen per each your application thread. And it's cost nothing for your application, and it's pretty can easily include it in your thread dump. So debugging of production issue can be significantly simplified. However, the biggest problem of this profiler. This profiler is built on libanvind library. This library is used to unwind your stack. And as you can see that basically instead of nice pretty Rust symbol names, we got just random addresses. So first of all Rust code is built with position independent code. And position independent code is very friendly with recent security features in Linux, which call address space randomization. So this randomization basically will load your program every time at each new address in the memory. And this prevents basically your application from any shellcode, because for the hacker will be pretty difficult to basically build very stable shellcode without any stable addresses where he can link and then run his code. So as solution for this problem, basically you can use static relocation model. In this case, you disable also security stuff. However, it requires rebuild your Rust toolchain with also system dependencies. And this is possible. However, in some cases, you don't want to waste your working days just to maintain your own Rust build. So we definitely switch to the next one. However, we still use for as our main allocator in our production. So bytehond, as I mentioned, this profiler written in the Rust, and it doesn't have any issues with unwinding stacks, and it's also super fast in comparison to Valgrind in no binary instrumentation, and also very smart hacks to capture, to reduce captured stack size. So it definitely looks as our first choice. Also, it can stream profiling data to your local machine. It's basically pretty similar what you expect from any profiler in JVM Vault. It just streams in real time your data to your PC, and then you see it immediately. You don't need to log into production machine, then load files and open in the tool. So looks nice. And one small positive is basically has web GUI, so you no need to try to build your KDE tool on the Mac machine and spend again some working time just to build in your tools. So in the end, it looks perfect, except this inability to capture stack traces on big heaps. So I hope maintainer will find the solution. Unfortunately, we didn't find how to solve it. This just switch to next one. So heap track. Heap track, same fast as bytehond, has pretty good, much more advanced GUI for analysis. The one drawback, which is not critical but still very convenient in production, you cannot just attach heap track on active process. This feature is quite unstable, and we face similar as previous reporter that during attaching your process can just fault it and you lose all your data. So we just run it in standalone mode. It's mean we stop applications, run heap track as preload library, then again take some data, stop application without heap track, and yeah, that's how we right now live. So once you did these pretty tedious steps, basically you can have very detailed statistics with allocations, which can just be used in your analysis. Some people may say it's still not user-friendly as Java, but in comparison to other tools, it's still, I think, very user-friendly. So, okay, once you did memory profiling, the next one is CPU profiling. CPU profiling is significantly more easy than memory profiling. However, it's still a little bit not so friendly as in JVM Vault. since again, it's rely on profiling tools. So you may face some difficulties with setup, like Intel Vatulin, very user-friendly and advanced profiler, which I would say even outperforms in terms of features any Java profiler, which is obvious since it's very close to hardware. However, it requires some drivers installation in hypervisor. And most probably your infra team will be not happy to do it. So the next one is Performance. It's main profiling tools, which basically just not require any installation or customization from your infra team and almost from you. And the last one, eBPF. This is pretty exciting stuff. Unfortunately, it will be not covered fully in this presentation. However, it will be future of continuous profiling, and definitely this will outperform in terms of features any Java profiler that you face. So, okay, let's start with perf. As I mentioned, perf is just work out of box. However, there are one important setting that you must to set. It's how you capture call stack in order to print basically all your stuff. So default one that perf provide you is frame pointers. Unfortunately, many compilers, especially Clang and Rust, they just omit frame pointers. So basically, in that you will not have any profiling information. So you can again fix it by rebuilding your toolchain with this forcing frame pointer settings. However, again, probably you don't want to maintain your Rust toolchain. So the next, you will definitely choose the next method, which is LBR, last branch record. And again, it's super fast because it's rely on Intel hardware registers. However, if you want to have at least some portability and run your application on AMD processor, then it's not your choice. And the last one, the dwarf method, which stands debug with arbitrary records formats. This method basically tightly coupled with debug symbols in your application. And unfortunately, it's the slowest method, but it's most reliable since, again, it's work with debug symbols from your application. However, even this method at current moment requires some tweaks. So unfortunately, latest version of Rust accidentally did some regressions, and they upgrade Clang to the latest version. And the latest Clang uses debug version of basically fifth version. And this version not supported by all Linux distributives. So most probably you don't want just to get your symbols go on all machines and upgrade everywhere Linux kernel. So most straightforward way, you just downgrade your Rust compiler, and then that's all. So the last option that you need take think is stack size. Since basically dwarf copy for each call part of calling stack, you basically need to specify how much perf should copy of this stack. So obviously, if you specify a quite small stack size, then profiling will have lower overhead. However, in this case, you might have a situation, especially with the sync code, when your huge call stack will be split into different branches, and in the end, it will, in your flame graph, it will mislead in your investigation. And last step, which required for post-processing, is just small tweaks for security Linux kernel attributes, just to enable symbols and performance events. So once you did all this step, you will get this pretty nice and detailed call graphs with user space and kernel space code. So fortunately, it will help in your investigation. So you may think, okay, once I get some results, why I need to dig down? So that's where eBPF came. It stands for Extended Berkeley Packet Filter. And initially in the old Linuxes, BPF was used only to monitor your network stack. However, in current Linuxes, basically eBPF can monitor absolutely everything: I/O, memory, CPU, events, network. So you will have full visibility over your application. And that's why I say that this level of visibility will be never achieved by Java profilers. However, it's kind of like cutting edge technology and still basically hard to set up. But I believe it will be pretty easy. Another one, when I mentioned why eBPF is future of continuous profiling, it's how basically classic profilers work. So they basically provide to the Linux kernel some huge buffer where kernel will populate it with some events, and then this buffer back to your profiler, and then profiler will basically render it or write to log file. And this process includes a lot of kernel and basically context switching between kernel and user space code, and it just naturally kill your performance. So with the BPF, basically you write a special basically programs that aggregate your kernel events in some quite small aggregated state, and you can do it, by the way, in the Rust and C, but Rust much more friendly to do it. And you just load this program into kernel, and since kernel provide you safety mechanism, it's perform validation. So basically, you will never get a fault in your kernel. You will never kill your system. So once you load it, then basically your user space profiler, tracer, whatever, can take it in aggregated form and also in async stuff. Since recent Linux kernel include such data structure as called ring per buffer, but in reality it's just multi-producer single consumer queue. And this queue basically almost eliminate any context switch between kernel and user. So you can have less than 1% overhead in overall profiling. And basically it means you can just never turn off your profiling and have full visibility what happened with network, with memory, with CPU. So almost awesome. So to summarize our experience with Rust. So first of all, you should never choose Rust for business applications because your product owner will basically be not happy if developers will say, oh, sorry, I cannot deliver because I fight a few days for how to compile this program. Another one, you should be ready to dig down in Linux internals. At the same time, as positive note, Rust provides you significantly higher performance with quite low memory usage in comparison to .NET or JVM. And another positive, most of Rust dependencies written by quite hardcore geeks, so they care a lot about performance. So you just get a lot of exciting libraries just for free. At some point, tooling, as you can see, kind of like immature and inconvenient in comparison to JVM. However, from our experience, writing non-flaky performance tests are much more simple in the Rust than in Java. And in the end, eBPF basically will this war, and then, yeah, there will be no drawback when used to Rust. So, yeah, thank you.